In one of the last videos I showed you how large programs can be broken into different translation units, which is useful for larger projects because you don't want to have everything in just one file. It would be very hard to keep track of what is actually going on. You want to split it into different translation units so that you always can focus on what is essential for a certain task. For breaking programs into translation units, I was using this example here, which is not that large, but is sufficiently large to give you an idea how things work. In this example, we ended up with two source files. One source file essentially just did contain this function main, and the other source file did contain this part with this definition of this global variable foo and this function bar. And the reason to split it like that was that function main was using what was defined above here. Now for making things work, we also needed this header file. Let me show you what we actually ended up with in the end. We had this header file here, used by both of these source codes. You see that it's included here in foobar.abc, and it's also included here. In larger projects, these header files have a similar meaning to a table of contents for a certain source file. So for example here, we could say this header file describes what is provided by this source file foobar.abc. And in some other source files, you simply want to use the functionality provided by some other source file. So when we think of the test program, it's simply using the functionality provided by foobar.abc, and for that you have to include the header file. You have to include what is provided somewhere else. So essentially we came up with some rules, some recipe for how to deal with projects where you have more than just one source file and header files. And one rule, for example, was that if you want to use functionality implemented somewhere else, then you have to include a corresponding header file. That also means that if you, for example, here implement things that can be used somewhere else, you have to provide a corresponding header file, like this header file. And in this header file, you have to declare everything that can be used somewhere else as extern. For example, somewhere else, this global variable foo can be used, and this function bar. And then another rule was that if you provide a header file, you also have to include your own header file. Obviously, we simply can write down these rules so that we actually have a recipe or a checklist, and then you can go through this checklist one by one. And if you follow these rules, everything will work. For example, here, the rules state that if you have a source file that exports functionality, so this source file is doing that, then provide a header. So we have a header here. So this is done. Declare in the header what is provided. Well, we provide this global variable foo and this function bar. All declarations should be marked as extern. Done, done. Always include your own header. Done. Inside the source file, include other headers as needed. Well, for example, here in the source file, we use printf here and here. So that's why we have to include standard IO. And we also use this global variable foo and this function bar. That's why we also include this header file. And because we followed all these rules, we now can compile the source files with ABC, followed by the source files. So in this case, foobar.abc, followed by xtest underscore foobar.abc. And this will work. The compiler will generate an executable called a.out, and you then can run this executable. So if you are good in memorizing things, and if you don't have a problem with blindly following orders, then actually you can now stop the video. Because in the rest of the video, I will just talk about the reasons for these rules, why they are necessary, and the reason for that is that I personally prefer to understand why I should do certain things, because then it's for me easier to memorize these things. And I also see an advantage that if I get an error message because I was missing something, I sometimes understand from the error message what I did wrong. another advantage is that in C and C++, basically the same rules should be applied because the C or C++ compiler works in a similar way like the ABC compiler. Now, to understand the reasons for these rules, it's actually very helpful to have some kind of understanding what actually happens when you translate the source files into an executable. And for that I will show you a few examples in the terminal, showing you how to use different options to actually see what happens. One option, for example, is the option -v, which is short for verbose. And with that option, you see that actually the compiler is just one part in the game, which translates each source file into an object file, and then a linker gets invoked, which links together all these object files together with some libraries into an executable. Okay, so let's translate the source files into an executable by also specifying this option -v to see what actually is going on, which certainly looks scary. But before we go here into the details, let's see that we actually have now this executable a.out, which actually can be executed, and when you run it, it's printing something. Now, to show you that, first of all, just 3 commands were executed one after each other, let me remove the a.out file and then I copy paste these commands. So this is the first command that gets executed, and then in this second line you see the second command that gets executed, and after executing these 2 files, still no a.out is in the current directory. This file a.out gets generated by the third command, which is the linker. And now we again have a.out as before. Now, to show you the essentials that actually just 2 object files were generated and then linked together, I want to redo basically everything, but in a easier to follow way. First, I just want to generate an object file from foobout.abc, and I can do that by simply using abc together with the name of the source file and the option c. And after that, you see we have this new file foobout.o, the object file generated by the compiler. If you want to see what actually is going on, you again can use this option -v, and then you see, for example, this here was internally added, which is a search path for header files. All the header files that you specify within angles are searched for in certain directories. In this case, in this directory, user local include abc. Also, this option here for specifying the name of the output file was internally added, which is simply the name of the source file with a different extension, the extension O. With object dump, you actually can see the content of the object file together with the option -d. You see that foobout.o just contains machine code. For example, this here is machine code for one instruction. This here shows you the assembly notation for this instruction. This is another instruction, and also this. And these are the 3 instructions for function bar. You also see that this here is something in the data segment. It's basically 4 bytes for the variable foo. And you see here the value hex to A, that's in decimal 42. So now we also can generate an object file for this source file. Again, specify the name of the source file together with the option -c, and then you see we have another object file here. And again, you can use object dump to actually see what this file contains. And it's containing a bit more, but you see here, this is the machine code for function main, and this here is machine code for the string literals. Okay, now let's also link together these object files into an executable, and you simply can use abc as a wrapper for the linker. And now I'm specifying just the object files, and after that we have the executable a.out, which again can be executed and does the same thing as before. by the way, to see that you're actually using just here the linker, but ABC as a wrapper for invoking the linker with all these options, you again can use this option -v. So you see this is actually going on behind the scenes. And here it's also important to understand that we are just linking together machine code, which is independent of the language that was used for generating this object code. So you also can use, for example, GCC as a wrapper for linking together this object files, for example, like that. And then you also get a.out. And here, if you also use the option -v, then you, for example, see that GCC on a Mac is actually Clang. And this is the command that was executed, which is identical to what happened up here. Actually, on my computer, I also have GCC installed, the real thing. So let's also do that. And then you see things look different. For example, here, the linker from GCC was used, not the linker from Apple. But again, we have a.out. Let's prove that. I first delete it. Use GCC version 14 to link together things. And then I again have a.out. And by the way, the linker is a very platform-dependent tool. So if you're not using a Mac, things completely look different on your machine. So this is another reason why you want to use wrappers which are hiding all these platform-dependent options. Now, why is this background useful to understand how header files are used to exchange information? Well, you saw that when you translate this source file foobar.abc into an object file, the compiler basically is just using foobar.abc for generating the object file. The compiler has no information about the test program. Also, when you translate the test program into an object file, the compiler has no clue about the content of foobar.abc. So all these things in here are completely unknown to the compiler. It has to generate object code independent of this other source file. And the header file comes into this game for exchanging information between different source files. And then you also saw that when you link together these object files, the linker has no idea about what you have written in your ABC file. It is just seeing machine code. Stupid, plain machine code. If you think that this is already complex, how these two source files are translated into an executable by first generating these two object files and then linking together these object files, let me actually show you the real thing. Because when you generate an object file, this actually happens in different stages. There are three tools actually involved. First, a preprocessor is used, which is handling, for example, all these include directives. And then a compiler is seeing the result of the preprocessor, generates some assembly code, and then some assembler is generating from that actually the object file. And I will show you actually the result of each stage. For example, the result of the preprocessor you can see when you specify the option -E, which I guess is short for expand. Then you can use the option -S to see the assembly source. And then you already saw that with the option -C, you can see the result of the assembler, which is actually the object code. So let's first see what the compiler actually sees when you translate the source file foobar.abc into an object file. So that's what the compiler gets. Let's compare it with the content of foobar.hdr, the header file, and the content of foobar.abc, the source file. And then you see this include directive was simply replaced by the content of the header file. That's it. Now let's also see what the compiler generates, the assembly code. This generates a file called foobar.s, and that's the content. So here you see a description of the text segment. Most important here is that we have a label for function bar, followed by some assembly instructions for this function. And here we see the description of the data segment, which also contains a label for the global variable foo. And here you see the initial value 42. And then you already saw that with -c we can generate an object file and look into it with object dump. So that's the same thing as before. And then we can do the same thing for the test program. First look into what the compiler actually gets from the preprocessor, which is now a bit longer because we include standard IO header, which includes other headers, and this is what in the end gets passed to the compiler. So from this, the compiler generates assembly code. Which is this here. Again, some description of the text segment with function main. Again, a label for this function followed by instructions for this function. And here you see the description of the data segment, which contains two labels for the two string literals that are used in a program. One string literal here and another one here. And then, of course, for completeness, we also can look into the object file. Same as before. So now the compiler has generated these two object files. And now if we use ABC as a wrapper for the linker, these object files can be linked together with some libraries into an executable. And again, if you want to see all the details, use the option -v. And then you, for example, see on my machine, also this library gets linked, and also the ABC standard library, the system library, and so on. So now let's summarize a few of the things. From this foobar.abc, this object file foobar.o was generated. From the test program, this object file was generated. That means we have two translation units. The first translation unit actually is the header file of foobar and the source file of foobar. Because what the compiler sees after the preprocessor is done is this part followed by this part. And from what the compiler gets, it generates assembly code, and this assembly code gets translated into machine code, which means we get this object file. So this object file contains machine code for the text segment, in this case the instructions for function bar, and it contains bytes for the global variable foo. So we have basically just an array of bytes. But actually we have a bit more in the object file. We also have the information that, for example, these bytes in the text segment did follow a label bar, and these bytes in the data segment did follow a label foo. So in the object file, you not only have this single bytes for instructions and data, but also this bookkeeping, this positions of these labels. And actually you can use a command called nm for name and give it as argument an object file, and then you will see this symbol table, this bookkeeping information. I'll show you how this looks like on my machine. So this tells me there is some label actually called underscore bar at address 0. So this could be fixed to underscore bar, and this refers to the first byte in this array of bytes. And there is also a label underscore foo. So this also could be fixed at address hex 10. So that means this underscore foo refers to the byte at address 16, hex 10. And that's basically it. That's the essential information here. We have an array of bytes, and we have positions for certain labels. Then we have the second translation unit, which consists of the included header files and the source file for the test program. Then again, assembly code gets generated, and from that, this object file. And again, in the object file, we have an array of bytes together with a symbol table. Now, if you look at the symbol table using the nm command, then things might look different on your platform. For example, on Linux, you will probably not see these two symbols. But you will see certainly a symbol for main, maybe without the underscore, which is located in the text segment identified here by this uppercase T. And in this case, the symbol main again represents address 0. And again, on my platform, actually, the symbol is underscore main. And then on my Mac, I also see this symbol here, which is actually used for this string. So this string is located here. And this symbol underscore .L0 is identifying the beginning of this block where the string is located. And this string here is located here at underscore .L1. But even if you do not see it, I didn't see it on my Linux machine, note that the letter here in front of the symbol is a lowercase letter. And lowercase letters mean that they refer to some internally used labels. Labels that are not relevant for linking and actually are ignored by the linker. So basically you can do as if you don't see it, even if you see it. The important thing is actually that you certainly have symbols with an uppercase U in front of them. And that means that these symbols are needed to make things work, but are not given in the object file. What does this actually mean? Well, for example, we were calling function printf. That means we have somewhere in the text segment a jump instruction to the address of the function printf. But in this translation unit, function printf is not defined. It's just declared. We just have the declaration of printf up here. That means when the assembler generated machine code, it couldn't plug in the address for printf. It did simply leave it out. It was using, for example, zeros. And that means we have here something that needs to be fixed by the linker. And actually we have the function called printf twice. So we have two holes in the text segment for calling function printf. We also have something missing. This variable foo is also just declared. So that means somewhere we have a fetch instruction. We want to fetch data from this unknown address foo into a register. And this fetch instruction happens before we call function printf the first time. So let's say here. And we also have another function called bar, maybe here, which also could not be generated completely by the assembler. The assembler again had to leave out the address. That means in this text segment we have several unresolved labels. And that's what you see here in the symbol table. So that means if we just look at the two object files and the symbol tables, we see that the object file for the test program has 4 holes. This hole here would be for fetching data from address foo. And that means basically this should actually fetch data from here, from the other object file. This hole here would be for printf and this here for calling function bar. So that means we should jump here to there. And then we also have 2 calls for function printf. Printf is somehow located, the machine code for printf is somehow located in a library somewhere else. But think of it that there is also some symbol printf which points to the corresponding instruction where the printf function begins. That means we should have also jumps to this location. Now let's look what the linker is actually doing now. The linker generates the executable, and the executable also consists of a text segment and a data segment. Now the interesting thing is that this text segment consists of the text segments that the linker found in all the object files and the libraries. So you see, for example, this part of the text segment in the executable comes from here. And this part of the text segment comes from here. So from these 2 object files, we have these 2 parts in the text segment in the executable. And this part of the text segment comes from the libraries. Also for the data segment, this part of the data segment comes from here. And this part of the data segment comes from the libraries. And then we also have to think about the holes that need to be fixed, that actually need to be linked together. So for example, here in this text segment, we have 4 holes. Then for example, here we have this fetch from data foo. So here we actually should plug in the address of foo. Here we have the function call to bar. So this should be fixed with the address of bar. And then we also have this function calls printf. So maybe this here is the location for function printf in the part that comes from the library. And with that, the linker can generate an executable which actually works. So that means in this executable, all symbols are resolved. Now, when I look at the symbol table of a.out on my machine, I see the following. There is in the symbol table a symbol for main here in the text segment, also for bar here. Then there is another symbol for the text segment, which points to address 0. I also have a symbol foo in the data segment, and then I have this internal symbols L0 and L1. But the important thing is printf is still unresolved. The reason for that is that the code for printf is on my machine located in a so-called dynamic library or shared library. Both terms are common. Shared library is more the Linux term. Dynamic library is more common for Mac and Windows. Well, about shared libraries or dynamic libraries, these are libraries that get linked to the executable when you start the executable. And the reason for using this kind of libraries is that it's saving disk space. If you would link this code for printf statically into each executable, then basically each executable would have the same piece of code for printing stuff, which makes each executable a bit larger. Actually, on Linux, it's still possible to also link everything statically into the executable. You can use the option -static for that. And then you can see the following. At least in my example, I saw before with shared libraries, I had 17 kilobytes. And afterwards, with static linkage, I had 190 something kilobytes. So you see the difference is quite significant in this case, even if it's still small. Another significant difference is the number of symbols that you then find in the symbol table. Here you just see the first few lines, so this is really much longer. For example, the symbol for printf I found in line 1500 something. But then, after static linkage, you have an executable that is self-contained. It really contains everything that is needed to run the program. Alright, so now we have a good understanding what happens when we translate these two source files into an executable. The first translation unit is actually this here, which generates some object file. The second translation unit is this here, which generates another object file. And then the linker is linking together these two object files into a.out. Now let's consider what happens when we do not include our own header file. Then we end up with that. The first translation unit is now just this file because it's not including the header file. And this works fine for the compiler. It generates an object file with the symbols. The difference to before is that these symbols are now internal symbols. You see that we have now lowercase characters here in front of the symbols. The default in ABC is that if a global variable doesn't have an external declaration, it's an internal global variable. If a function doesn't have an external declaration, it's an internal function. That means in this case the symbols for these functions and variables are not visible to the linker. The second translation unit is this part here. From that, an object file with these symbols will be generated. And you see, as before, bar, foo, and printf are undefined symbols, but no compile time error. Then we try to link these object files into an executable, And now it's important that the linker is not seeing actually these two symbols because they are internal symbols. And that's why you get an error message from the linker. The linker complains that the symbol bar and foo is undefined because the linker doesn't see that these symbols are actually in this object file for foobar. And that's it. Yeah, that's why you should include your own header file, because then the compiler is seeing these external declarations, generates code where these symbols are visible to the linker. Let's look at another example where we have a function dummy here and a function dummy here. So in both source files, we have the same name for a function. Now let's see what actually happens when we translate this into an executable. In the first translation unit, we just look at this part here, and then you see that dummy is not an external symbol, so it's just used internally, and that means the compiler simply generates the function call. It can resolve this function call, and the linker will not see the symbol dummy. In the second translation unit, we also have a function call to dummy, to this here. Here also dummy is not an external symbol, so the linker will also not see the symbol dummy here. And that means the linker will not complain. What the linker is seeing is, as before, that bar foo is undefined, but it's defined here and here. And also printf is undefined, and this is defined in the libraries. The symbol dummy is actually not visible to the linker, so the linker doesn't see any conflict, and it's generating a.out, which is executable and runs fine. Now let's get crazy and use an external declaration for function dummy, but not in the header file, in the source file foobar.abc. And let's see what happens. So this here is the first translation unit. The compiler generates an object file for it. In this object file there is a call instruction for calling function dummy, which will call this function here. That is the same as before. The difference is that now this symbol for dummy is also visible to the linker, but that's actually the only difference. The second translation unit is this here. And here the symbol for dummy is internal because there is no external declaration, and as before, this function call simply calls this function. And that's it. So what has changed is that now this symbol dummy here is visible to the linker. Does the linker have a problem with that now? Well, the linker first checks if every defined symbol is unique. And for that it of course goes through the list of visible symbols. So this is visible to the linker, this is visible to the linker, also this. This here are unknown symbols. So it basically just checks all the symbols with an uppercase letter except for an uppercase U. And then it's checking whether it can resolve all the unknown symbols. So for example, bar can be resolved, foo can be resolved, and printf is defined somewhere in the library. So the linker is fine with that. It generates a.out, and this can be executed and works fine. Now let's get a bit too crazy. We declare here this function as an external function, and also here, so in both source files. Now when we look at the first translation unit, basically the same happens as before. And in the second translation unit, now almost the same happens as before, but also this symbol dummy is now visible to the linker. It's now visible in both object files. And this should give us a name conflict. And that's exactly what you see here in this error message. The linker is complaining here, not the compiler, that the symbol dummy is not unique. The linker first checks whether all these visible symbols only show up once. And the symbol for dummy is now showing up twice. Now the bad thing about linker errors is that they are not very nice to read. I mean, you basically get a message in the form of something went wrong, but you don't get a message like it went wrong here and here because you defined it here like that and somewhere else differently. or you declared it here the first time and here a second time. So what you want is that you get the error message from the compiler, not the linker. And in some cases you simply can avoid it by never using an external declaration in a source file. For example, move the external declaration into the header file, like here. Then the following happens: the compiler will try to generate the object file from this translation unit, which actually works because here the declarations do match. In both cases, you have one parameter and a return type int. So an object file gets generated. Then in the second translation unit, the compiler is seeing this code. And here the compiler will complain that this here is not matching with the previous declaration. And you get actually line numbers and visual hints what went wrong, that these two declarations do not match. So this is much nicer. However, you cannot always avoid it. For example, in this case here, we have in the header file the declaration for dummy with one parameter of type int, return type int. So this here also matches. So that means from that the compiler will generate an object file. When the compiler looks at the code for this translation unit, then it also works because this is also matching. It doesn't matter that you use here and here different names for this parameter. I mean, in a declaration, the parameter name is anyway optional. So the compiler will generate also for this second translation unit an object file, and in both object files now the simple dummy is visible to the linker. And that means you again get a linker error because the simple dummy is not unique. Now this problem is a bit harder to avoid in general. Let's actually go back to the slide where I can show you the source code. Now this is actually a real-life problem. Think of it as follows. You want to write a program, and this program for some reason requires a global variable foo and a function bar. And then you find this nice library which provides a header, like here. But let's say it not only declares in the header file 3 things, but actually hundreds of things. 2 of them you actually are interested in, the global variable foo and the function bar. And you haven't seen this declaration for dummy. So accidentally you also declare and define a function in your program with the same signature. Then the compiler will generate from your program an object file with a visible symbol to the linker dummy. And then you have also the object file for that, and then you have this name conflict when you link together the object files. Now how can that be avoided? Actually, you have to hope that whoever provides this header file uses something like prefixes. For example, if this source file here is called foobar, a prefix could be fb_. So that means this symbol here, foo, actually should be something like fb foo. So whatever you declare in here should be prefixed with fb_. And this here, fb dummy. So that means every symbol that you export begins with fb_, and that means of course that you also have to change things here. You have to change this here, and this here. And then you can avoid the name conflict when linking things together by simply not using the prefix fb_ in your program. In C++, there is a language feature called namespaces, where basically the C++ compiler is doing that for you. The C++ compiler is prefixing all the symbols within a namespace. In C and in ABC, you have to do it manually. And of course, you also can use other naming conventions. You could agree that everything ends on _FB, something like that. But you need some kind of discipline. And yeah, as I said, it's a real-life problem. Now let's also look at an example where no header files are used at all. I actually want to show you here that it might work, but it's actually dangerous. So you are really playing with fire if you're not using header files. So this is the first translation unit, and from that the compiler will generate an object file with these symbols. So a symbol foo and a symbol bar, both of them are visible to the linker. And this here is the second translation unit. It's generating this object file with a simple main visible to the linker, and these unresolved symbols. So here the linker perfectly can link things together and things will work. Because basically we just have included by ourselves the header file into the source files from the example where everything worked fine. So you can execute a.out and it's working. Now let's change a little thing which motivates why you actually should use header files. Somehow the person who implemented foobar came up with the idea that bar no longer should be a function which always returns just a constant value. The person who implemented this source file changed it into a global variable. Now the person who is using this source file, the person who is implementing this translation unit, did not get the information that bar is now a global variable. Now what happens is the following. The compiler generates an object file from foobar.abc with two symbols visible to the linker. And the second translation unit generates an object file with the symbols as before. Main is defined, visible to the linker, bar and foo, and also printf is undefined. Now recall that the linker is just dealing with object files, and object files are just arrays of bytes together with some symbol tables. And the linker is not knowing about the meanings of symbols. The linker is just looking at symbols in order to fix holes, to patch bytes in this object files. So the linker checks are there name conflicts, which is not the case here. Then it's checking whether it can fix all the holes. And the hole for bar can be fixed by using the symbol here. The hole for foo can be fixed by using the symbol here. And the hole for printf can be fixed by using whatever address is defined in these libraries. And that means the linker will simply generate a a.out. And this a.out actually can be executed. And that means you can translate these source files into an executable. And there is no warning or error from the compiler or the linker. And you get an executable that can be executed, and it even runs for a while, and then it simply is crashing. No hint about what is actually the problem. Now obviously the problem is that when this function gets called, it's actually a jump into the data segment to this global variable bar. And this is where this bus error comes from. But by just looking at this part here and not knowing all the details, you basically have no chance to fix that error. And here you actually should appreciate that sometimes you get error messages from the compiler or the linker. And for getting these error messages, this help about what is actually the problem, you have to follow the rules.